Hello everyone, my name is Dongping from Northwestern University. My collaborators and I evaluated the utility of conformal prediction sets for AI-advised decision-making in an image labeling context. We're interested in this problem because in real world, we always pair humans with the AI for complementary performance. Because ideally, human-AI team should achieve better performance when compared to human judgment or AI standalone accuracy. So to facilitate AI-advised decision-making, it is important to quantify uncertainty and make predictions more transparent and explainable. But uncertainty quantification is difficult for neural network predictions because of their black box nature. These models typically have complex architectures and it involves millions or even billions of parameters, which makes it hard for us to understand the underlying logic behind their predictions. So what are the possible ways to quantify prediction uncertainty for neural networks? One common approach is to present both the model's top K predictions and the softmax pseudo probabilities, which indicate prediction confidence. The problem is, softmax are not reliable. Prior research in machine learning has shown that neural networks have a tendency to output overly confident predictions, even when the model encounters instances that they are unfamiliar or unseen during the training. Also, unlike conventional confidence intervals, top K predictions does not provide any accuracy guarantee. That is, for an unknown instance, decision makers never know whether the true answer is included in the top K predictions that are presented. Another possible approach is to construct Bayesian neural networks, so that predictions depend on sampling from the posterior distributions of model parameters, which makes them carry an inherent measure of uncertainty. But Bayesian networks heavily rely on prior assumptions and are computationally intensive to train, especially for deep networks. Given these challenges, conformal prediction is a more effective and efficient solution that can be used to quantify the prediction uncertainty by the use of prediction sets. The framework is compatible with neural networks because they are distribution-free. That means the validity of the sets does not depend on any distributional assumptions about the data or the model's parameters. What's more useful is that conformal prediction sets are like a type of confidence intervals, which presents a set of predictions with a coverage guarantee that the true answer is, on average, captured within the set with probabilities such as 95%. Therefore, prediction sets can be designed to express uncertainty through its adaptiveness. For example, as images are getting increasingly harder for the model, prediction sets will express more uncertainty by including more predictions to ensure the coverage guarantee maintains. So what makes prediction sets adaptive? The adaptiveness is realized through an inductive conformal procedure. To do so, we need to present a calibration dataset which contains similar but unused data points when training the model. Let's suppose we have a pre-trained convolutional network that can classify images for a simple label space of 5. And let's say there is a calibration instance with a known label of a cat. So what conformalization does is we sum the ranked softmax up to the true class, which are colored in red. This creates a conformity score, and this score captures the model's accumulated confidence for this instance up to the correct classification. After conformalizing all images in a calibration set, we have a distribution of conformity scores. Now recall the coverage guarantee. The key takeaway from this distribution is to identify a conformal threshold. Say we want 95% coverage, we set alpha to be the 5% quantile, which indicates error tolerance. We can now use this conformal threshold to create adaptive prediction set for test images. Suppose we have a new cat and we feed this image to the model, and we include all classes whose predicted softmax exceeds the conformal threshold. This inductive conformalization is what makes a prediction set adaptive and express uncertainty. Now we know how prediction sets work, but here is the problem. In real world, a deployed model can commonly encounter challenging instances such as those affected by data perturbations or simply out of distribution. These instances will lead to large sets that express high uncertainty. As shown in this example here, larger sets can increase viewers' cognitive burden for navigating the set and finding the correct answer. So showing uncertainty information may compromise decision making. We have virtually no knowledge about how well people can interpret and use prediction sets in the decision-making pipelines. So we want to explore what prediction sets actually enhance AI-advised decision-making better than the status quo top K predictions, and how well people can deal with increased set size due to adaptiveness. To answer these questions, we conduct a large-scale experiment on Prolific with a pre-registered analysis plan. We recruited 600 participants and asked them to label a unique set of 16 images sampled from ImageNet. Our participants were randomly assigned to 4 display conditions, so they either label images with no prediction, which serve as a baseline, or label images using displays showing conformal prediction sets, or the status quo top 1 and top K predictions with softmax pseudo-probability. We manipulated image stimuli by considering real-world use cases. Because a deploy model can often encounter out-of-distribution instances that the model is not trained or calibrated for, we transform some images out of distribution by applying synthetic image corruption. At the same time, since the classifier can have varying confidence in predictions, so we group images into easy ones and hard ones by using the cross-entropy loss derived from our base classifier. As previously mentioned, prediction sets can have varying sizes based on difficulty, so we further categorize image stimuli by set size into smaller ones or larger ones within each difficulty type. We selected 10 stimuli for each predefined group, which leads to a total of 80 candidate images. And our participants were tasked to label 16 sampled images in a randomized order, 1 from each in-distribution group and 3 from each out-of-distribution group. We focus on 3 response variables, which are accuracy, shortest path length, and willingness to pay. We measure the shortest path length between the selected label and the ground truth label as defined on the wordnet hierarchy, which is commonly used to quantify the semantic similarity. The willingness to pay is a measure that we elicit from participants at the end of the experiment, which captures how much they are willing to pay for the prediction displays if they were to repeat the study with a similar distribution of instances. To summarize our results, we find when stimuli are in distribution, prediction sets don't offer much value over top 1 or top K displays. However, smaller prediction sets appear to be more useful, potentially due to lower cognitive burden and the coverage guarantee. When stimuli are out of distribution, prediction sets had slight advantage over top K displays, regardless of their set size. We think this is because out-of-distribution images are naturally more challenging for both humans and the model, so they always result in larger sets. In this scenario, decision makers can extract useful information or hints from those inaccurate predictions included in the set that serve the purpose of uncertainty quantification. Additionally, we find participants place roughly equal value in all prediction displays, as the distribution of willingness to pay are quite similar. However, humans have a tendency to over-rely on predictions even when the model are underperforming. We only observe complementary performance from the top 1 condition, and we think this is because when humans are able to immediately detect inaccurate predictions, they are more likely to rely on their own judgment, which can actually lead to better performance. To summarize our study, we evaluate the utility of conformal prediction sets for AI-advised image labeling. We find set size is a critical determinant of utility in that a smaller prediction sets, in general, can lead to similar or slightly better performance than the top K displays. We find the value of conformal prediction set depends on the properties of the setting, because we see prediction sets can outperform top K displays and can support robust decision-making when instances are out of distribution. Therefore, we think when designing predictive interfaces, designers can hugely benefit by considering to present predictions and visualize uncertainty based on instance type, and treating instance detection as a model's learning problem. Thank you for your interest in our research. I'm happy to take any questions you have.